Hello and welcome to this webinar on results interpretation and overview. My name is Mike Fiedler. I'm a designated support specialist at Autodesk, and I'm going to work with you on today's presentation. Today we're going to work with Inventor Nastran, and we'll take a look at some of the tools that are available within the results environment and how you can really investigate the results of your analysis. So let's go ahead over to Inventor and take a look at what we're going to do today. This is the subassembly that we are taking our parts from, and for the model that we're going to work with today, we're going to take a look at the arms and this cross member here. So I've already set that up. Let me go over to the Inventor environment. Basically, I just narrowed it down to this subassembly, and then I've already moved it into the Inventor Nastran. If you need to know how to get there, it's from the environments, and then you can access Autodesk Inventor Nastran. And I've already set up this model, and I'll explain what I have done to set it up. So the first thing that I did was define the material. Let me edit this, and I want to use a 36 material. So let's access the steel ASTM A36. Scrolling down the list here. There we go. And we'll say OK to that. And I've already added constraints, and you can see I selected the cylindrical regions here, and I assigned them pin constraints. So the constraint type of pin is selected, and I've fixed radial and I've fixed the axial directions. And we'll say OK. And I did the same thing in two other locations. So there's mid-upper, which is right here. And then we have mid-lower, which is here. And they're all pin constraints where I allowed the tangential direction movement. And the reason that we have to do three different ones is because whenever you utilize a pin type of constraint, it's basically saying that we have some sort of bearing or axis that the model we're going to control the radial, the axial, and the tangential directions, right? Basically, these are three different axes. If you imagine passing a cylinder through those regions that we have constrained, we cannot use the same pin type of constraint for all three of those sets. So I had to break them up into, again, three different applied constraints where the ones that I have chosen all would have the same cylindrical axis. But no big deal. It doesn't take a whole lot of time to set up. And then as far as the loads at the front end of this, where the bucket would be, I applied a minus 15,000 pound force load. Now, when I had set this all up, we'll take a look at the mesh settings. The mesh settings that I did, element size of 2 inch, and I just generated the mesh. In the settings, maybe we could say to project the mid-side nodes, generate that mesh. And now, because it is an assembly, we also have to worry about the contact. So as soon as the meshing is done here, we'll take a look at that. These are all the different contacts that are in the model. And if I select one, it highlights on the model. And I'm leaving it at the default type of contact, which is a bonded type of contact. And I didn't specify any other parameters. So what is controlling that? Analysis settings. And we can take a look at the options tab. And on the options tab, we can see that it's a default of bonded, and then a tolerance that it's using. And it says, you know, if some nodes or nodes in a surface are within that distance, when we go through the automatic contact to set up the pairs of contacts. And what I had envisioned whenever I first ran this analysis was that, you know, I would just go ahead and run it, and then whenever we start the presentation, we can jump into the results environment and begin to take a look at the results of our analysis. As it turns out, this turns out to be a very good example of some issues that you might encounter. So if you've gone through the slide deck that accompanies this learning material, one of the things that I mentioned is potentially when you're going to review the results, you could run into an issue where you don't obtain results on your analysis. And that is actually what happens with this particular model as it is. So you can see here the Nastran solution failed, and there was an error shown there. So where is that? What I can do if I want to get back to that information, I can go to the Nastran Output tab, and you see here that we have a fatal error. It's an E5004 error, and stiffness matrix singular, non-positive definite. And when this error occurs, being that it's a fatal error, I don't get any results. So the goal today is really to focus on our results, but with my analysis set up as it is, we don't have any results. And what I mentioned in these slides, whenever you encounter a fatal error of the E5000 type, generally what you can do, or one thing that you can do, is to run this as a modal analysis. And then in the modal analysis, or from the results of the modal analysis, usually what you see is that some part moves by itself, shakes free because it's unconnected to the rest of the geometry. So that's typically what you'll see when you have an E5000 error if you run a modal analysis. And so what I did was I selected the analysis. You can right click on the analysis and you can say that you want to duplicate the analysis right there. So that is what I did. Let me activate this second analysis of ours. And then I just change the analysis type that we're running. If I go into normal modes here, access normal modes. When I access normal modes, all I did was, or I should say after I duplicated the analysis, I accessed the analysis type, and then I just changed it from a linear static to a normal modes or natural frequency analysis. Now, in this one, let me say OK to that or cancel out of that. And make sure my material set to the same material. It does copy over the loads and constraints. Running a normal modes analysis, it isn't going to worry about the loads. That's fine. We're just looking for the natural frequencies. But it's nice that it copies the material. It copies over the constraints for me. So there shouldn't be anything that I need to do otherwise for the setup. What I can do is just go ahead and run the simulation. Okay, so our normal modes analysis is finished. Let's say OK to that. And here's an analysis, being that we didn't have any fatal errors, an analysis that we can review some results of. All right, so when we take a look at the results, when it comes into the results environment, by default, the normal modes analysis is going to calculate for me 10 different modes. And the way we can access the different modes would be from the pull-down menu here in the results of the ribbon bar. And when there is an issue with the model in a natural frequency analysis, when there is, and by issue I mean there's rigid body motion, that is, something is just translating or rotating about its axis, basically unconnected to ultimately the constraints, the ground of the model. Usually what happens is the frequency ends up being 0 or very close to 0. So in the normal modes analysis, when it comes into the results environment, it's showing me the last mode that it calculated, mode 10, which shows me a real frequency of 26 hertz. But if we look at the first couple modes, mode numbers 1 through 5 or 6 or 7, in fact, the first 8 modes are all very low frequency. So if I go ahead and I click on mode number 1 and allow it to show me what that mode shape looks like, and there, again, we're looking at mode 10, the bending of the arms, first bending mode of the arms. There you can see in mode number 1 something that we didn't see in the initial assembly, right? There's a cylindrical part here, and what we can see is that it's got some translation. It's just moving out of the assembly. And then I could take a look at mode number 2, so I can tell, okay, this part, why is that moving? It should be connected to the rest of the structure here, but it doesn't appear to be. And there's the second cylinder, or cylindrical part of this assembly, and it also is just translating. So I can see that I have problems with both of those. And then as I go through these different modes here, that just kind of confirms what we are seeing, but it doesn't hurt to go through the different modes. And there's something that I talked about also in the slide deck. Whenever things are rotating, they seem to expand. And if we take a look at the displacement, what we're probably going to see is some concentric pattern of displacement contours. All right, so there we can see that. So those parts are just rotating. So basically at this point I know that at least those two bodies are not connected to the rest of the geometry. The contact is not there for those parts. So that means that I need to do something to tidy up this model. And when we go into, what are we on, fourth mode here, now you can see that they're just basically vibrating free from the rest of the structure. So again, my constraints are here, in this location here, and this location here. These two parts didn't have any direct constraints on them, so the only way that they would be fixed to the rest of the assembly would be through the contact. So I need to make sure that whenever I define my contact in this assembly, that these two parts are tied into the rest of it. So what I did then was just go ahead and hit return, and then again I right-clicked on the modal analysis and I duplicated that. So let's go ahead over and take a look at this model. And I'll tell you what I did. So this one I renamed to modal redo, and this is where we start to investigate, how do we fix this assembly so that those parts are tied into the rest of the structure. And basically what I did was I went back to the modeling environment and I hid this arm, this plate metal arm, and then I could see where these cylindrical parts were supposed to tie into these gussets here, right, and then also tie into this bracket here. And if we zoom in there, hopefully you can see that right there. You can see that there is a gap between them. So with that gap in there, that gap is larger than the tolerance. Again, let me double click on the analysis and go back here to options. So this bonded, automatic bonded that gets done in this tolerance here is 4/1000th of an inch. But the diameter of these tubes is smaller than the diameter of these holes that it sits in, both in the gussets here in the center and on the end plates, if you will. So that contact never got added. Those parts are, the names of them are PK46.25.01.007, and I also checked that out when I was back in the modeling environment. And when I came back and I expanded my list of surface contacts, I could look down the list here so you can see everything is 46.25.01. And again, those individual part numbers are .007. As I scan through this list here, they just didn't exist in the list. So from the automatic contact, they were never picked up, again, because they were outside the tolerance of what the program is going to create for contact pairs. So what I did was I set up some manual contacts. You can just click on manual, and I selected the one entity being the cylinder, and then for the second entity, the surface that I needed it mated to. So I went through and I did that for each of those two tubes. And if we edit that, so you can see there's one of the pairs. There's the tube, there's the surface that it should be mated to, and I used a offset bonded contact, and then I gave it a activation distance, a tolerance to utilize that is slightly larger than the gap between those two parts. And then I did it at this location and then the two end plate locations. So for each one of these tubes, you have 4 different locations. So that's right there. And then the second 4 for the other tube. And basically what I would do is I would just, change my parameters and then keep working within this particular scenario within this particular analysis until we make sure that our model is all connected. So I'll let this analysis run, and we'll be able to see the differences in the outcome or the results of this particular modal analysis. Okay, so the normal modes analysis with our additional contacts added in has now completed, and we can take a look at the results of that analysis. Let me zoom out here a little bit. And again, we are starting at mode 10. So let me go to the pull down menu. And we can see now, if we look all the way down, the frequencies will be sorted in ascending order. So the first mode would be your lowest frequency, your second mode, you know, a little bit higher, the same, or a little bit higher, and so on as you go up through the modes. So now we can see that mode number 1 is the 26 hertz, which is the same frequency that we saw before for the arm. So that's going to be my first mode now, because we eliminated those rigid body modes. And when we look at the results of our modal analysis, we expect to see more of a global level mode shape versus an individual part like we saw before. So this tells me that my geometry is now connected together. I don't see any parts flying off into space. If we, again, take a look at our mode shapes, well, I can tell by the frequency that it is connected, but that gives me some confidence. So we can see the first frequency, 26 hertz. The second frequency is also 26, very similar frequency. So that's just going to be bending of the other arm. I'll just toggle into that and see that. So I hadn't intended to necessarily show modal analysis whenever I was first envisioning this particular webinar, but it's good that the model ended up doing this so that I could show that modal analysis is a great way to figure out, potentially where there are parts that, if you have a large assembly, you may not have initially noticed that there were parts that were unconnected. So I wasn't the one that constructed this original geometry, or if I were, I certainly would have been aware of that coming into the model setup. And I would say it's probably not uncommon that somebody provides you with an assembly and says, here, run this, and maybe initially you're just presuming that all the parts are touching, but as we know, that's not always the case, because there could be interference, there could be gaps as we saw here, because ultimately later it's going to get welded, or maybe some other component gets fit in there, some bushings or bearings that weren't initially included with your model. But anyway, at this point we know that our assembly is all connected. So at that point I'm ready to go back and perform my linear analysis. So what I maybe would have done in a normal situation was just gone back to my linear static analysis and made those changes there, but I wanted to preserve that so I could show that to you. So what I did was I made another copy of this particular analysis. I just right-clicked again and said duplicate, and that's not a terrible way to approach this, and I'll tell you why. Because when we make a copy of that modal analysis then, and I change it back to linear static analysis, that carries over the surface contacts. So, I added in those 8 additional surface contacts, and those just get copied over into my linear static analysis. So, saves me a little bit of work of having to reset them up. So that's a good thing. And show you that in a moment. There we go. There's the different surface contacts that I have included there. Did that kind of quick. There you can see the manual surface contacts that we defined versus the rest of the list here was created via the auto option. So at this point, the fact that my modal analysis runs and all my geometry sticks together, if you will, or is connected together, that tells me that for this linear static analysis, everything should just as well stick together, and we'll run that, and then finally we'll be able to take a look at some results beyond the modal results. Okay, so my linear analysis has completed, and we can get into the results environment and begin to take a look at some of the things that we want to take a look at typically once we get into the results environment. So As we come into the results environment with a structural analysis, the Inventor Nastran is going to show us stresses, and that's a decision by the product team. And I think the thinking there is, generally people want to come in, they very quickly want to see what their stresses are. Are they below the yield of the material? Do they have high stresses, in which case they know they need to make some sort of change? And if I go into the pull down menu as I just did there, going to stresses, I can take a look at the solid von Mises. So von Mises are generally comparable to the yield, and yes, we can make uh, the quick assertion there, or presumption there, that I'm using an A36 material. I see that my stresses here are about 6,700 roughly. We can also see that that's within a notched area. Might have a bit of a stress concentration there. But I can see that I'm well below the yield of this material, so that's good. But as I mentioned in the slides, for this particular learning content, was I would propose that one of the first things that you do is take a look at the displacements, because the displacements, with a linear static analysis, we know that we want the displacements to be relatively small, and they should be logical as well, right? So by logical and small, we'll talk about that a little bit. First of all, they are small, relatively small displacements. The overall length of these arms is roughly about 10 feet. There's somewhere about 4 feet between the first and second hole there, and then about another 6 um, between the middle hole and the where it would attach to the assembly as a whole. So again, roughly about 10 feet in length, and we can see with the given loads, again, somewhere around 15,000 pounds, that my displacements are about 3/1000ths of an inch. So nice small displacements, so we haven't violated any of the basic presumptions of linear static stress, which presumes a small displacement, right? And when I look at the displacements on the geometry, the other thing that I see is I have a gradient, right, going from a maximum displacement near where my loads are applied down to essentially zero displacement where my constraints are applied. So, that looks good to me too. I don't see any one individual part which has some massive displacements on it, which would indicate also that it's not connected to the structure if some component was able to just fly off in the space. So that tells me that it's all connected together. Now, one of the other things that I mentioned in the slide deck was that by default, when we change to the displacements, it's going to show me a total displacement, which is a square root sum of the squares of the x, y, and z components. So if you want to look at individual components, you can certainly do that. So I could take a look at, say, for instance, the x direction along the x-axis. And because the total is a square root sum of the squares, it's always going to be a positive value. But when I go to one of these vector components, then I'm going to get both positive and negative values. So I can see that as I add this force in the minus y direction, we have both some positive x movement. If you look at the mini axis down here, we can see that this end of it is kind of moving in the positive x direction, and then the portion of the model, or some nodes of the model in this region, are moving in the minus x direction. So that makes sense given the constraints and the loads that are on the model. And with, again, any of those vector directions, you're going to get positive and negative values, presuming that the loads and the constraints that you have on the model are going to influence the geometry to do that. Of course, if you have something like just a bar, and you add constraints at one end and a tensile load at the other, I wouldn't expect to see both positive and negative values along the axis of that bar, right? So, just taking a look at the y direction, again, we can see that along the back end of it, given the pin constraints allowing the rotation that we have, the back end of the arms move in a positive y direction, and then where we have the load, we can see that we have a minus y direction displacement. So in this model, that doesn't matter too much. I just wanted to show you that you can look at vector directions. And when that does become important, again, given the constraints that you have on it, given the loads that you have on the model, sometimes it causes these displacements in a certain vector direction. And it could be relatively small, but in something like, say, an electronics package, where your deflections are coming from thermal expansion or contraction, or something with some tight tolerances, sometimes the displacement that results could cause some interference. Maybe we don't have 3/1000ths of an inch clearance between this component. Certainly we do in this, a front loader model, but in some other assembly or product, you might not have 3/1000ths clearance before this. These nodes would impact something else. So it doesn't hurt to take a look at it, and it's certainly doable. The other thing that I would say is the one that we didn't explore here. If I go to the next one over the pull down menu, if I want to change that from English inch units to, say, something metric, if you need to share your results with somebody who works in a different unit system, you can very easily, very quickly toggle it to a different unit system. Okay. So that's enough with the displacements. The next thing I wanted to show, let's take a look at stresses. Now, stresses are going to be very similar in that when I go to stress, and if I go to the pull down menu here and I change this to say a von Mises stress again, the von Mises stress is going to be something of a square root sum of the squares type of computation. So the results are always going to be positive. If we take a look at the lowest von Mises, it's somewhere right around 0, and then my max is going to be 6,697. Right, and again, that's because of the square root sum of the squares type of solution that it's doing, calculation that it's doing. But if you take a look at some of the other results that are here, say something like a x normal stress. So any of the normal stresses or principal stresses are going to yield both positive and negative stresses, which would give me an indication of, in the case of the solid x normal stress, the tensile and the compressive load. So here, if we zoom in here, you can see in the red area, 6,000, that's in tension. And then, of course, given the load at the end, that's going to put these elements into compression. And if we take a look corresponding to the blue, there I can see I have results that are somewhere around the negative end of the spectrum, indicating that those are in compression. So that's maybe a good point or a good time for me to show some things about inquiring results at specific locations of the model. And there's really two different ways that we can do that. So one of the ways that we can do that is by going up to our ribbon bar in the results panel. Right here, there's an icon that says probe. And if I go ahead and I select that and I just move over top of the model, you can see that the indicator here is telling me what the results are. So if I just hover there, it tells me what the element is that I'm hovering over. The result type that I'm looking at is an X normal stress, and then what the value is at 3470. And I don't necessarily have to be right over top of a node, so it can interpolate from the nodes that are around it what the value is at that location. And again, you can see if I wanted to figure out, is it in fact in compression and what is its value, it's showing me that it's a minus 3458 in that area, right? And as I move it around or away from the elements of compression, we can see that value is reducing ultimately until we reach an area where it switches over to elements that are in tension. Now, let me turn off that probe. The other way that you can interrogate is to go up to nodes. Right? If I right click on nodes, then I can choose query display. And then I'm going to move over top of my geometry. And the node query is just going to give me results from nodes. So if you're out in space somewhere between a couple nodes, it might not give you a result. But if you're on a physical node of the mesh, or you're on one of the mid nodes, it'll tell you what the result is at that node. You can see that it's telling me specifically the node number, the coordinate locations of that node, the translations of those nodes, X, Y, Z, and then since we're on a solid X normal stress, what the result is at that particular node. So that one is more useful if you're looking at specifically a specific node. And sometimes, you might have forced a specific location. I can go in and I could split a surface to make sure that I have a node in a specific location. So if I know, for instance, that I wanted to get a value here that was maybe, I don't know, 4 inches up and 4 inches over from this hole, because we're going to put a stress gauge on there, then I could split this surface back in the modeling environment to make sure that I have a node at that specific location, and then I could always do a nodal query at that location to figure out what the stresses are, and then I could match that up between my finite element analysis and what the experimental results show me, or the physical testing results show me. So 2 different ways to go about that. Just wanted to show that. As far as other results are concerned, we took a look at displacements, we took a look at the stresses here. I'm not going to go through all the stresses. There's quite a large list of them. What I will mention is you might also want to take a look at your strains. And let me toggle over to a strain result here and go to the pull down menu for just a second. When I go to strains, when I go to the pull down menu, you'll notice that it's lacking in options. And that's because the program by default doesn't output all the different types of strains. Should have turned that on before we ran the analysis, but it wasn't on, so I did that intentionally so I can show you where that option is. Let me double click on the analysis type. If I do want all the strain output, again, when I go into my analysis options, we can check the box for strain, which is not on by default. We'll say OK. And I do need to run the analysis with that option on, so I'll let this analysis run. We can take a look at that. Okay, so that analysis is finished. And we will take a look at those results. So I wanted to show this because sometimes people go to access the strains as far as interrogating the results of their model, and they say, how comes I don't have any value here? And it's because you need to invoke that option before you run the analysis. So pretty simple thing to do. It's just a matter of remembering to do it before you run the analysis. And then we can access all the different results there. So I could take a look at, for instance, my X normal strains at this point, and then everything that we took a look at just a moment ago. You can do the same thing with the strain. So I could use the probe tool. I can go in and I could take a look at the nodal query, so on and so forth. So make sure that you turn that output on if that is a result of interest. What else might we want to do? It might be interesting to take a look at the support reactions. So as far as support reactions go, so for instance, maybe I'm trying to size the hydraulic cylinder that's going to be utilized to connect between the main assembly and these connection points here for lifting this subassembly. So it's another good thing that I broke up the constraints into 3 different groups, and I named them appropriately. So this constraint group was called mid-upper, middle of the assembly, and the upper constraints versus the lower constraints. And as far as getting the reaction forces, if you right-click, what you do is just access SPC summation, and you can see that it selects all the faces that were involved in that constraint group, and then it tells me what the total force is at that location, 813, and the loads in the X direction, the Y direction, and the Z direction, and likewise I can figure out what the moments are at those locations as well. All right, so then I could take that information, and maybe that's what I utilize as information to help size what that hydraulic cylinder is going to be. And you can also select multiple too. So if I select the first one, I control select the second one, I can do an SPC summation, and then you get the total of the upper and the lower ones that I'm using there. So in force, I'm seeing a total reaction force of 4,329, and then the component directions as well. So SPC summation is another good tool that you will probably utilize with some frequency. Now, the other thing that I wanted to show as far as interrogating results would be the graphs, and as they're called in Inventor Nastran, the XY plots. But they're probably more interesting, as I mentioned in the slides, when we have something that is either a time-dependent analysis, such as a transient thermal, or if we get into something like a nonlinear analysis where there are steps involved, so the load is increased incrementally, if you will. So right-click on that analysis, and we do a duplicate here. Let me move into that analysis, activate that one. And so I wanted something interesting to happen with this analysis. And we saw from the results of that linear analysis that our results were somewhere around the 6,000 mark, between 6 and 7,000. So if we expand the material here, after changing this to a nonlinear static analysis, I'm going to change the material. Just right-click on the material and say Edit. And I'm going to select a new material from the Autodesk material library. Not that you would ever design, the structural portions of a front end loader like this, but just so we have some interesting output here, I'm going to change the material to copper. And when I change it to copper, you can see the yield stress on this material is at 4,829, right? So it's lower than the stress results we get with these forces at the front end. And so the other thing that we want to do, or that I already did, I went into nonlinear, and I told it that I want it to be an elastoplastic or bilinear analysis. So that way, it's going to follow the modulus of elasticity up to the yield point, and then it does have awareness of what that yield stress is at 4,829, and then it's going to follow the slope defined by the tangent modulus. And at that point, we can go ahead and run that analysis. Okay, so that analysis is finished. Let's say OK to that. And now we have the results of our nonlinear static analysis. And I wanted to do a nonlinear static analysis because it is an analysis type that has multiple increments, much like if you do a transient thermal analysis. The transient thermal analysis would have multiple solutions over a function of time. So when I set up my nonlinear analysis, I told it that I wanted it to solve in 10 steps. So what that does for me is it breaks up that total load into those 10 increments. Of course, in the first increment, you can see the load is 0.1 or 1/10 of the forces applied, and in the second increment, the 2/10 of the load, and so on and so forth. So I can always roll back through the different increments and loads and see, at the fourth increment, for instance, or 40% of the load, what are my stresses, what are my displacements. So that's one of the nice things with a nonlinear analysis. You can kind of control the progression or the application of the load and see how the geometry responds at those different increments of load. And a different way to toggle back and forth between the pull down menu here, of course, is the previous and next buttons, which is maybe just a faster way to do it. Otherwise, you do have these same tools that we looked at with the linear analysis. We can take a look at the probe tools. We can take a look at the nodal query tools. You still have the same pull down menus here, so you can toggle through the different results. But just a couple other things I wanted to show beyond the fact that there are multiple increments. When we get into the initial goal of running this as a nonlinear static analysis, you'll notice that you have XY plots, and it comes up with a number of default plots here for you. So you have, for instance, a maximum displacement versus load scale factor. And if I want to see what that looks like, I can just select one of the default plots here and say show XY plot, and it'll print that out for me. So there is the plot right there. If I wanted to, I could also change this up a little bit as far as what the style of the lines are or the colors. I can copy this information to a clipboard if I would like. If you don't see a particular plot here of what you want to see with your analysis, you can always right-click on the XY plot as well and say New. And that's going to open up your XY plot dialog. And the first thing that you have here is the choice between nodal information and element information. So nodal information, if I come in and I select a node here, and you can see it identifies that node, that would be utilized for certain types of data, such as displacements and rotations and forces and moments. You can see the information that it is able to plot by node. And in the upper right-hand corner here, this is the span over which you want to plot it. So I'm doing a multi-set plot where it's going to start at increment 1 and plot the increments 1 through 10, which would be the total increments from my analysis. And I can say show XY plot. And there I can see the displacement of that node over the 10 increments that I solved for. On the other hand, if you are looking for something like a stress, then I would go into an element selection, and I'm going to select a element in that area where we saw the max stress occurring. And I'm going to do something like, let's do a X normal, and again multi-plot or multi-set, and I can say show, and there is a nice plot. We can see of course, we changed it to a copper material. We told it that that copper material was a bilinear material. So once it reaches the yield point on the material, then we can see how it changes slope once it's exceeded the yield of that material. So XY plots, nice tool, something to keep in mind for certain analyses that you're going to do. Okay, so I would like to show just one more function within the results here. And I can get there via a couple different ways. Maybe one thing that I do is just go to the results panel in my ribbon, and I'm just going to go ahead and click on the options here. And that brings up this plot dialog. And so with this plot dialog, I can set up a couple different things. First, I can tell it which increment, because again, this was a nonlinear static analysis with 10 outputs. So I can choose which subcase I want to see. I can tell it what result data I want to see from the contour option. So maybe I want to see displacement, and then I can tell it, again, similar to like we saw before, do I want to see total or specific along a specific x-axis. I can also control the min-max as far as what the legend shows me, if I wanted to specify that. You can come into the deform options here, and deform options allows me to control the displacement. And this was something that I talked about in the slides as well. So when you're doing a nonlinear static analysis, it doesn't exaggerate the deformed shape of the geometry. It's going to set it to actual displacement 1 times the actual displacement or deformation of the model. And then when I'm ready to have the program show me that, I can just go ahead and click on the display button, and then it'll display the output according to all the settings that I have checked. Okay, so there we are. So there's increment number 10. It's showing me the displacement values and the actual displacement on my geometry. Okay. There are other things that you can do in here. You can create section views. So if you want to show a section view, you click on the checkbox there. You can tell what plane. You can drag the planes around to slice through the model. There's part view options here, so I can click that, select the part, and then I can isolate the display of my results to the individual part. You can get into vector options if you prefer to see things in vector form. You have animation options here, so you can tell it how many frames to output, and then create the animation. But I'm going to do one last thing. Let me cancel out of this, And let's say we wanted to go back and look at something with one of our linear analysis. So let me right click on, or left click to highlight that analysis. Then I'm going to right click and I'm going to say I want to activate that analysis. So this analysis, having already run it, I don't want to have to run it again to review the results. So I know that those results exist, and this would come up, when you toggle back and forth between the different analyses, or maybe you save your work, you go home, you open it up a couple days later. How do I get into these results? If I right click on the results, what I can do is a couple different things here. One, I can do show in folder. And if I do a show in folder, that takes me to the results folder and specifically highlights the .fno file, which is related to this particular subcase and analysis. So I could find where that file exists, so I know that that file exists. The other thing I could do is I can just right click on results and say that I want to load the results, and that will load up the results for that model. I know that the results are available because they're no longer grayed out here. And then what I can do is either just right click and say that I want to display one of those results types that are here for me, the von Mises displacement safety factor. It'll take me right into that result type. Or again, similarly, I can go up to the menu bar and get into my results options again, just like we did for the nonlinear static. And whenever the plot comes up, again, just like we saw before, I can go in and I can say, okay, maybe here I want to see a stress or a strain result. Let's do a stress result. Let's toggle it to say that we want a von Mises stress. There it's telling me what the max and min is going to be. And again, I can adjust it if I want. Maybe we'll do that. Let's specify. And we'll say at the low end, we want to see data min of 0. And at the max end, let's say 7,000. And I'm going to go into my deform options. Deform is already checked, so that means it's going to show me a deformed or displaced shape. Now notice the difference here. In the nonlinear static, it was set to actual and one time. Because the linear static, the displacements are going to be relatively small by default, we're going to exaggerate them. So it's setting it to 10 times a scale of the model, the largest dimension in the model. And so if you want to change it, I'm going to leave it at that, but if you want to change it to see the true deformed shape, you can click on the actual button and set it to 1. But with linear analyses, we're always going to scale it up. And at that point, I think I have everything set that I want to display. So we'll go ahead and click the display button. And I'll say OK. So there we go. There's we're in a von Mises stress. I set the min range to be 0, the max range to be 7,000, even though the true max on my model is at 6698. We're just adjusting the range of the legend, so you can certainly do that. There's one other thing that I don't think that I talked about in the slide deck, and I guess it's the last thing that I can think of that maybe I want to show you. Maybe the final thing that you're going to do is prepare some images, or you want to show somebody the model and you'd like to clean it up a little bit. The last thing I'll leave you with is there's a number of options here under object visibility, and that's where we can turn on and off the display of certain things. So maybe I want to get rid of the min-max markers. That's right here. I can just uncheck that. Cleans up the model a little bit. Sometimes I like to get rid of the mesh, the display of the mesh. Just makes it a little bit easier to see the contours. So we can turn that off, and that'll clean that up. And then lastly, the red lines here, which show the initial position of the geometry, that's your undeformed edges. So we can turn that off as well. And there we go. So that's that. We could also do things like turn off the constraints and the loads if you also want to clean up those also. But I think that's pretty good right there, and you get the point. So hopefully that helps to highlight, some of the major points of what you'd want to do in a results environment. We showed you how to change different results types. We showed you how to inquire on specific points in the model, how you generate the XY plots,